So far, all of the integers that we've been looking at have been the so-called decimal numbers, right, that we're all used to using. In the decimal system, each digit represents a certain number of a certain power of 10. For example, a number like 8,529 is saying that this number represents 8 thousandths plus 5 hundredths plus 2 tenths plus 9 ones or units, which would be 10 to the 0. Right now, notice how every number here is based on some number of powers of 10. Thinking in powers of 10 is convenient for humans, not so much for computers. For computers, on the other hand, with their very on-off structure, right, a binary or base 2 number system makes a lot more sense. So where decimal or base 10 numbers are made up of 10 different digits, 0 to 9, binary numbers use only 2 digits, 0 and 1. So interpreting a binary number is done the exact same way as a decimal number, but using powers of 2. Right? That means that this number represents 1 times 2 to the 0 plus 1 times 2 to the first. Oh, that's a little out of place there. 1 times 2 to the first plus 0 times 2 squared plus 1 times 2 to the third. Right? And if we add all of these numbers up, this is 8 plus 0 plus 2 plus 1, we get 11, right? The equivalent decimal value of that binary number. Now, there's one important detail that you need to be sure to notice, right? It's this little subscript 2, right? This is telling you what the number's base is. Right? Now, it's a small thing, but an important distinction. If you accidentally leave that off, this would turn this from a base 2, a binary number, back into a decimal number, right, with a very different value. Okay, so how can we go the other way? Right, from a decimal number, like we have here, to a binary number. Well, what we need to do is write this number as the sum of different powers of 2. Right, and so let's see. The smallest power of 2 less than 11 is 8. So I would start by writing this as 8 plus 3. Right, now I'm kind of done with the 8. I'm just going to keep bringing that down on every step. Right, now 3 is smaller than 4, so I'm not really going to be able to get a 4 out of this, but I want to write it in there, right? I want to write this 8 plus 0 times 4, right? And just bear with me for a minute. You'll see why when we get to the last step, right? Plus, now I can't take a 3 out of that 2, right? I can write that 3 as 2 plus 1. And now 8, 4, 2, and 1, those are all powers of 2. Right, they can be written as powers of 2. For example, now watch what I'm going to do here. I'm going to make this 1 times 2 to the third plus 0 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0. When you notice how similar this is to the decimal number we looked at on the very first slide, right? Only instead of having powers of 10, I have powers of 2. And just like with that decimal number, it's the numbers that are out in front of the powers of 2 that are going to make up my final result. So what I would say here is that 11 is equivalent to 1, 0, 1, 1, base 2. Right? And that's how we convert from a decimal number from a binary number into a decimal number. Okay, so in the next lecture, we're going to look at an application of this, right? We're going to see how we can take information and encode it, if you will, into a binary number, and then use logical ands and logical ors to take that binary number and evaluate it to see, to get that information back out.